The systems we have seen so far in this class have all been linear systems because every equation in them has been linear. Any system of equations that contains at least one nonlinear equation is referred to as a nonlinear system of equations. So you do not need every equation in a system to be nonlinear in order for the system to be considered nonlinear. As long as you have even one nonlinear equation in the system, then the entire system is considered nonlinear. Many nonlinear systems can be solved using the substitution and elimination techniques that we learned for solving linear systems. We will learn how to solve such systems in this section. Let's go ahead and try to solve this equation. We notice that we have y, which is easy to solve in both of these equations, the top one being our nonlinear equation, the bottom one, of course, a familiar linear equation. The system, however, will be considered nonlinear because of that top nonlinear equation. So it's usually going to be easier if we solve the simpler equation. In this case, it'll be this linear one for one of the variables. So we'll go ahead and solve that for y, and we end up with y equals 8 minus 2x. Now we can take the 8 minus 2x and substitute it for y in the first equation. So we end up with x squared minus quantity 8 minus 2x equals 0. Very important to put parentheses here because you need to distribute that negative into both terms. So we end up with x squared minus 8 plus 2x equals 0. So we're going to go ahead and put that in descending order to prepare it for factoring or solving by other means. It does look pretty simple. I think we'll be able to factor this. So let's go ahead and use, it's a lead coefficient of 1, so that means we can use our little cross trick here, right? So we want the product to be -8, the sum to be +2, and I think you'll agree that +2 and -4, actually the other way around, right? -2 and +4 should do the trick. Notice the product is -8 and the sum is +2. So that means x minus 2 times quantity x plus 4 should factor that for us. We do a quick check always. First times first is first, last times last is last. Inner and outer products add up to the middle term, okay? So either x minus 2 is 0, we're now applying the 0 factor property, or x plus 4 equals 0. So this gives us either x equals 2 or x equals -4. Now each of those are going to generate a new y value for us. So this is of course the ideal equation to use to get y because it's already solved in terms of, for y in terms of x. So let's go ahead and see what happens if x equals 2. That implies y equals 8 minus 2 times 2, which is equal to 8 minus 4, which is 4. And if x equals -4, we're going to get y equals 8 minus 2 times -4. So that's 8 plus 8, which is 16. All right, so we have two solutions. The first solution will be the ordered pair 2, which pairs up with this 4, so 2, 4. And the second solution is the ordered pair -4, 16. Okay, do take the time to substitute those, this for x, this for y, into both equations to convince yourself that it works. Now, if you actually take each of those equations and solve it for y, for example, the first one becomes x squared equals y, and the second one becomes y equals negative 2x plus 8. Now if you take those and graph them, as we will in a second, okay, as you can see here, I've plugged them in to save us some time. Notice what we're finding is basically these points of intersection. That's all we've done. But we've done it algebraically. But it's always good to have an intuitive understanding of what it is that you're actually doing, rather than just going through motions and solving equations, etc. So that is what we are doing. All right, here's another one. Go ahead and try to see if you can solve it on your own first, then come back. All right, so again, notice we have one nonlinear equation, one linear one. We'll go ahead and solve the linear one for y, which is easier to do. So I'll just go ahead and move y to the other side, the negative y. So I get 3x plus 24 equals y. The negative y becomes y on the other side. So now we'll take that and we'll substitute 3x plus 24 for y in the first equation. So we get 3x plus 24 equals x squared plus 8x. Now we will go ahead and move everything to one side and get 0 on the other side, so we can get ready for factoring and applying the zero factor property. So we have 0 equals x squared plus 8x minus 3x and then minus 24, right? Be comfortable moving to either side, left or right. Sometimes people get too used to always moving variables to the left side. There's no mandate on that. All right, so we get 0 equals x squared plus 5x minus 24. Okay, let's go ahead and see if we can solve that. So we're looking for two numbers. Because the lead coefficient is 1, we can use this little help system that we have with the cross. All right, so we want two numbers whose product is negative 24, whose sum is positive 5. Okay, so it looks like negative 3 and positive 8 should be good candidates, right? So we have 0 equals quantity x minus 3 times quantity x plus 8. Now applying the zero factor property yields that either x minus 3 equals 0 or x plus 8 equals 0, or both, of course. So either x is 3 or x is negative 8. So now we need to find the corresponding y values, and of course this equation right here is the best one to use because it already expresses y in terms of x. So when x equals 3, that implies 3 times 3 plus 24 equals y, and that's 9 plus 24, so 33 equals y. Now when x is a negative 8, that implies 3 times negative 8 plus 24 equals 0, which implies negative 24 plus 24 is 0. Actually equals y, not 0. So negative 24 plus 24, that's 0, so we get 0 equals y. Okay, so we have two solutions once again. One of them is the ordered pair 3, 33. And the other one is the ordered pair negative 8, 0. All right, so you should go ahead and try substituting, make sure that it works. And you can also verify it on a graph. It's a similar situation. You have a line and a parabola, and we're finding the points of intersection. All right, in this next one, both of our equations are nonlinear. And if we apply the elimination method here, that tends to yield really good results. When both of them are nonlinear like this, we usually try elimination. So Let's go ahead and try to eliminate either x or y, x squared or y squared. I'll just go with y squared first. So let's go ahead and multiply the top equation by -3. If you think you know how this should go, then stop and try it on your own. Alright, so -12x squared minus 3y squared equals -3. Make sure you multiply that -3 by all terms because of substitution, and also the fact that we're multiplying on both sides. And the second equation we'll leave alone for now, so we get x squared plus 3y squared equals 14. Now we can go ahead and add the two equations, and we end up with -11x squared. The -3y squared and y squared, they cancel out, they become 0, equals 11. So we get x squared equals -1 if we divide both sides by 11. That means x equals plus or minus square root of -1, which, as you know, is also known as I. So x equals plus or minus I. All right. Now we need to substitute back in to get the values of y, and do notice that because the x is being squared, it doesn't matter whether I plug in positive or negative I, we get the same results. So rather than doing this twice and plugging in I once and seeing what we get, and then plugging in negative I, we can just do them simultaneously. So we go something like this: quantity plus or minus I squared plus, I'm just substituting into the second equation, plus 3y squared equals 14. Now, whether I square positive I or negative I, in either case I'm going to get I squared, and I know that I squared is -1. So I get -1 plus 3y squared equals 14. So we end up with 3y squared equals 14 plus 1, which is 15. So y squared equals 5, and that tells me that, applying the square root property, that y should be plus or minus square root of 5. Now do realize that we could have reached this result of this y value for either I or negative I. That means I pairs, x equals I pairs with both y equals radical 5 and y equals negative radical 5. So does x equals negative I. That also pairs with y equals radical 5 and y equals negative radical 5 for solutions. So we actually are looking at 4 solutions here, right? And we end up with the first ordered pair being I square root of 5. The second one being I negative square root of 5. The third ordered pair is negative I paired with radical 5. And the fourth one is negative I paired with negative radical 5. And that's all 4 of our solutions, okay? That's how you would approach that one. All right, so here's another one containing 2 second-degree equations, and again, it looks like a good candidate for elimination. We'll go ahead and multiply the top equation by -2. Notice we could have divided by 7, in fact, in both equations, to make the numbers smaller, but it's almost not worth the time. So we'll just do this. So we get -14x squared minus 14y squared equals, that should be 120 and then 6, right? 126. So we get negative 126 on that side. And this second equation, we don't change. All right, so we notice that we end up with canceling both the x squared and y squared terms on the left side. And on the right side, we actually don't end up with 0. We end up with, doesn't matter, but let's just do it for fun. So 6 from 12 is 6. Negative 63, right? So this is a clear contradiction. So this system is not going to have a solution. If we go ahead and graph the two equations, of course, it'll become amply clear why there is no solution. As you see here, they end up being a pair of what's called concentric circles, meaning circles that have the same center, and they of course have different radii, so they will never touch. So that's why that system would have no solution. So for the solution set, we put S equals the empty set. All right, or the null set. All right, let's take a look at this system. Now, if there is one of the two equations that happens to be easier to solve for one of the variables, we pick that one, and here they're both going to generate fractional results, so it doesn't really matter which one you use. Now, a note of caution on this one, some students look at that and go, well, that's linear, isn't it? So these are both linear equations. The first one is actually not, because to compute the degree of a term like that, you would actually have to add the degrees of the two variables. So this would actually not be a first degree term, it would be a second degree term. All right, so let's go ahead and solve that first equation for example, y. So we end up with negative 8 over x, right? So now we'll go ahead and substitute this negative 8 over x for y in the second equation. We always need to create this connection because remember, we're trying to find a point that's common to both of them. So when you solve one equation, you're obviously going to substitute in the other one. So we have 3x plus 2 times negative 8 over x equals 2. So we get 3x minus 16 over x equals 2. All right, now we can go ahead and as soon as we make the specification that x shouldn't be 0, because otherwise this term would become undefined and therefore the whole equation would become undefined, we go ahead and multiply both sides by x. So we get 3x squared minus 16 equals 2x, right? So 3x squared, let's move everything to one side, minus 2x minus 16 equals 0. All right, so this lead coefficient is not 1, so you do not want to use our cross diagram. We just are going to go ahead and factor using the trial and error FOIL method. So 3x here and x here. So there are different ways we can get 16, but experience tells me that 2 here and 8 here should work, right? Now notice that the inner product will be 8x, the outer product will be 6x. We want their sum to be negative 2x. Notice how I haven't put any signs yet until this point right here, but I know what I want the sign to be. So now I realize that I can get that negative 2x if I make the 8 negative and the 6 positive. So the minus should go here and the plus should go here. Okay, so I'm going to go ahead and erase this bottom part. That was just kind of like thinking out loud, right? Okay, so we quickly check. First times first is first, last times last is last. Inner and outer products do indeed add up to the middle term. So we've factored it correctly. So now we'll apply the zero factor property, which says either 3x minus 8 should be 0 or x minus plus 2 should be 0. So 3x equals 8 or x equals negative 2. Okay, now that we have, let's finish this actually. X equals what? 8/3, right? All right, so now that we have our x values, we'll go ahead and substitute. Right here it would be the best candidate because it's already solved for y in terms of x. So we'll plug in there. So we get if x equals 8/3, that implies y equals negative 8 over 8/3, which just means negative 8 divided by 8/3, which turns into negative 8 times 3/8, which is of course negative 3. Okay? And when x is negative 2, that implies y is going to be negative 8 over negative 2, which is positive 4. So we have two solutions. The first one being the ordered pair 8/3, which pairs with negative 3. So 8/3 negative 3. And the second one being the ordered paired negative 2, 4. Always write x first and then y. All right, so there's a good one. Make sure that you're comfortable with that and we'll proceed. All right, so here we have another problem. Now, we have solved something similar to this, but I wanted to give you a little bit of an alternate take on it. Notice that, for example, I could go ahead and solve the second equation for, say, y, to get y equals 20 over x, and then proceed like before. But I want you to realize there's also a way you can avoid getting that fraction by maybe squaring both sides of xy, right? So we get xy equals 20. So we get x squared, y squared equals 400, right? Now, do be aware that we're modifying that equation. So we have to be careful because we may get some extraneous solutions. So we'll watch out for that as we proceed. But this does kind of work out nicely because now if I take that top equation and solve it for y squared, I get 4x squared minus 39 equals y squared. So now I can go ahead and substitute 4x squared minus 39 for y squared in this equation. So I get x squared times 4x squared minus 39 equals 400. So distributing the x squared, I end up with 4x to the 4 minus 39 x squared equals 400. So if we move everything to the left side, we end up with 4x to the 4 minus 39x squared minus 400 equals 0. Now notice that this is the kind of equation we call quadratic in form, because whatever the variable expression in the second term is, when you square that, you get the variable expression in the first term, right? So this is quadratic in form, basically the ax squared plus bx plus c form, right? So that means we should be able to factor it like a quadratic, right? Now, you could use a u substitution, or you could just do it directly. I'm going to try to just do it directly, okay? So we're not going to use the cross diagram because this is not 1. So let's try maybe 4x squared and x squared. The product of those two does give us 4x to the 4. Now, I need two numbers here whose product is going to be negative 400, but I'm just focused on the 400 right now. I'll worry about the sign later, okay? So let's go ahead and find the prime factorization of 400. Notice that we can start with 2. 400 divided by 2 is 200. We write that here below the 400. And then we can use 2 again. That gives us 100. 2 again gives us 50. One more time gives us 25. Now we have to go to 5. That gives us 5. And then finally 5 gives us 1. So I noticed that these are the different ways. This is the prime factorization of 400. So I can do like 2 times 200 or 4 times 100, etc. But notice, I'm going to want my numbers to be a little closer to each other. So what if I look at that group, right? That gives me 16, right? And that gives me 25. Those are numbers that are relatively close to each other, right? So what if we were to do 16 here and 25 here? Now notice I'm not putting any signs yet. Notice the inner product will be 25x squared. The outer product will be 64x squared. Now, what do we want? We want negative 39x squared as their combination, right? So let's see if 64 minus 25 assists us, right? And I noticed that is 39, okay? So again, with experience, you get better at guessing what should go where. All right, so we noticed that we want a negative 39. So we're going to make the larger one negative and the smaller one positive, okay? So basically, we're going to have plus here and minus there, okay? Notice that this times this gives you 4x to the 4. Last times last gives you negative 400. Inner product and outer product, while being aware of the signs, do give us the middle term. Okay, so we have factored it. Now, sometimes, you know, let's say somebody is being very mean to you, it may not even factor, in which case you don't panic, you do a u substitution, and then you apply the quadratic formula, okay? So now we're going to apply the zero factor property, which tells me either 4x squared plus 25 is 0, or x squared minus 16 equals 0. So this one gives me 4x squared equals negative 25. So x squared equals negative 25 over 4. Applying the square root property tells me x should be plus or minus square root of negative 25 over 4, which is of course going to be plus or minus 5/2 I, right? Because of that minus inside the radical. All right. Now, from the other equation, we get x squared equals 16. Therefore, applying the square root property, x should be plus or minus 4. So now we want to see how these x values are going to work with corresponding y values, right? So I can see that once I have x values, this would be an ideal place to get my y values using this equation. So I'll start with x equals 5 over 2i, 5/2 I. not to be mistaken with 5 over 2i, with the I being in the denominator. That's very different. So this implies, let me clear the factorization of 400 quickly. All right, so this implies that y is going to be 20 over x, which is, of course, 5/2 I. Now, there's a little quick trick I want to show you. Notice if you have a over b over c over d, right? That means a over b divided by c over d, right? Which means a over b times d over c, which is AD over BC. So notice it means if you have A over B over C over D, you can quickly get to the answer by finding this outer product, putting it on the top, and this inner product and putting it down below. Okay? So that's a really useful trick to know. So let me go ahead and instead of 20, write 20 over 1. So now you know that's going to be the outer product, which is 40, over the inner product, which is 5i, like that, okay? Because remember, when you have 5/2 I, that's like 5i over 2, okay? So this I goes with the 5. Now, obviously, 40 and 5 are just going to cross cancel and leave you 8 on the top, right? So you end up with 8 over I. But that's not a form we usually like to leave that in, because we don't like to have radicals in the denominator, right? So we'll go ahead and rationalize. You may be thinking, what radical? Remember, I is what? The square root of -1. So there's a radical in the denominator. So the way to get rid of that, if you recall from our early work, is you go ahead and multiply by I over I, which gives you 8i over I squared. I squared, of course, is -1. So that's 8i over -1, which is -8i. Okay? Now, if x equals -5/2 I, we're going to get y equals 20 over 1 over -5i. Let me write it like this so it's clearer for you, okay? -5i over 2. So now the far product or the outer product is 40, and the inner product, or sometimes we call it the near product, is going to be -5i, okay? So the 40 and -5 give me -8, so I get -8 over I. We need to get rid of the I again from the denominator, so we multiply by I over I. So we end up with -I, 8i over I squared, which is -1. So I get -8i over -1, which is just going to be 8i. All right, let me erase the stuff down here. Okay, so now we move on to x equals plus or minus 4. So if x is 4, this is going to be much, much easier, right? That implies y equals, remember, 20 over x. So 20 over 4. So it's 5. And if x is -4, that implies that y is going to be 20 over -4, which is -5. So we're ready for our solution set. So first order pair we found was x 5/2 I and y -8 I. The next one we had was x was -5/2 I and y ended up being 8i. Our next one is the ordered pair 4, 5. And our last one is the ordered pair -4, -5. And that's it. That's how you do it. So practice this, see if you can do it all on your own, and then move on to the next one with me. Before we move away from this problem, I want you to notice that 2 of our solutions are involved real numbers and 2 are imaginary numbers, right? So notice that if you look on the graph, this will make a lot of sense. All right, so as you see, once we graph these two, as you'll find out, the hyperbolas is what they're called, you will notice that they do meet at these 2 points. But notice we had 2 other solutions which indicate those are not points that you're going to be visualizing like this on a real graph, okay? They're non-real complex solutions. Okay, so there we go. All right, here's another one. For this one, I want you to think a little bit outside the box because I want you to see if you can come up with a non-usual or unusual, kind of substitution. All right, so normally we just substitute for one thing, right? X or y or maybe x squared or maybe y squared. But this time I noticed x squared minus y squared here, and I notice x squared minus y squared here. So that's what I'm going to substitute for. So I notice that x squared minus y squared is -96. So I'm going to replace this x squared minus y squared in the top equation with -96. So we end up with 2xy, and we're going to replace that x squared minus y squared by -96, and we have equals -56. Okay, so we get 2xy equals -56 plus 96, which is 40. So 2xy equals 40, so xy equals 20. Now I can get a very nice simple expression for y in terms of x. So y is going to be 20 over x, right? And now we can just take that 20 over x and substitute it for y in the second equation. So we get x squared minus quantity 20 over x squared equals -96. So x squared minus 400 over x squared equals -96. We'll go ahead and multiply both sides by x squared. Of course, making note that x shouldn't be 0 again, because if it is, that's going to make this denominator 0 and this undefined, right? And therefore the whole equation undefined. So we're going to go ahead and multiply both sides by x squared. So let me just show it. That means multiply each term by x squared because of distribution on that side, and because of the fact that we have to multiply on both sides on this side. Okay, so we get x to the 4. Notice these two x squares will cancel out. So minus 400 equals -96 x squared. Now we'll go ahead and move everything to one side. All right, this is a much simpler factorization involved here. Notice it is quadratic in form. It's not quadratic, it's 4th degree, but it's quadratic in form. So we can factor it like a quadratic. So we'll put x squared and x squared here. Now, in fact, we can even use our cross diagram, right? We want two numbers whose product is negative 400 and whose sum is positive 96. What do you think? Did you say negative 4 and positive 100? I agree with you, okay? Notice their product is negative 400 and their sum is positive 96. So we get x squared minus 4 times x squared plus 100 equals 0. Now, if x squared minus 4 is 0, we get, well, zero factor property tells us that either x squared minus 4 is 0 or x squared plus 100 is 0, right? If x squared minus 4 is 0, that means x squared equals 4, so x equals what? Plus or minus 2 by the square root property. If x squared plus 100 equals 0, that means x squared equals negative 100. So x is going to be plus or minus square root of negative 100, which gives me plus or minus 10i, right? Okay, so we have, again, 4 x values, and we're going to find the corresponding y values, right? So if x is 2, that's going to make y, of course, substituting right here is the easiest place. Gives me y equals 20 over 2, or 10. X equals negative 2 implies y equals 20 over negative 2, which is negative 10. If x is positive 10i, that means y equals 20 over 10i, which is 2 over I, which we need to rationalize by multiplying by I over I. So we get 2i over I squared, which we know is negative 1. So we get negative 2i. And if x is negative 10i, that means y is going to be 20 over negative 10i, which is going to be negative 2 over I multiplied by I over I. So you end up with negative 2i over I squared, which we know is negative 1. So that's going to be end up being positive 2i. All right, so now we're ready to write our solution set. Contains the ordered pair starting with 2. So 2, 10, and then negative 2, negative 10, and then 10i and negative 2i, and finally negative 10i, 2i. And that's our last ordered pair. All right, so a pretty good problem. Make sure that you can carry that, and we'll proceed. All right, next we want to find the equation of the line that passes through the points of intersection of the graphs of these two functions. Well, not necessarily functions. The first one is a function. The second one is not. It's a circle, as you know. So we're basically finding the points of intersection of a parabola and a circle, and then we want to find the line that goes through those two. Well, we assume 2 points of intersection. And remember that we can only use real solutions here. So if we get any complex non-real solutions, we're going to ignore those. We don't even need to pursue them and find them, because we're only interested in a real graph with a real line that goes through 2 points with real coordinates. All right, so basically we need to solve the system, right? So we have y equals x squared and x squared plus y squared equals 1332. So go ahead and try it, see if you can manage it, and then come back. All right, so this is not actually one of the tougher ones we've done, as you'll see. Notice that since y equals x squared, I can go ahead and replace this x squared here with what? With y, right? So we end up with y plus y squared equals 1332. So y squared plus y minus 1332 equals 0 if we put everything on the left side and the 0 on the right side. So we need to factor that 1332. It's not that bad. If you just do the prime factorization, we start with 2 and divide and see what happens. So 1332 divided by 2, that gives us 666. Now we know that 2 goes into that again 333 times. Now 2 doesn't work anymore, but 3 does, right? That gives us 111. I know 3 goes into 111 because 1 plus 1 plus 1 is 3. And remember, if the sum of the digits is 3, that means the number is divisible by 3. So we get 37, and 37 goes into 37 once. Once you hit the 1 here, you're done with the prime factorization process. And on the left side here, you have the prime factorization of 1332. All right, so notice we're looking for two numbers whose product is negative 1332, but whose sum is positive 1, right? So these two numbers need to be really close to each other, right? So that's a 37. Let's see what the product of all that is. That's 4 times 9, so that's 36. That looks very promising, doesn't it? So how about negative 36 and positive 37? How does that look? That looks pretty good, because we know from the prime factorization that the product is going to be 1332, but because of the negative, it'll become negative 1332, and we know that the sum of these two numbers is positive 1. So we have found our factorization. So y minus 36 times y plus 37 equals 0. So either y minus 36 equals 0 or y plus 37 equals 0. Now, so I get y equals 36 or y equals negative 37. Now remember what y is. Y is x squared, right? So that means either x squared equals 36 or x squared equals negative 37. So that gives me x is plus or minus 6. And the other equation gives me x equals plus or minus square root of negative 37. These are, these two are non-real complex. So that means we can't use them, because we want points with real coordinates so that we can find the equation of a line going through them. So we're going to use these points. 6 pairing with 36 and negative 6 pairing with 36. So now think about this for a minute, what we're saying. So if you just do a quick sketch, let's say that's negative 6, and let's say that's 6, and not necessarily to scale. Let's say this is 36. So negative 636 will be like here, 636 will be right there. So notice the 2 points have the same y value. So this is going to be a what? That's going to be a horizontal line, right? It's a horizontal line going through y equals 36. So what's the equation? Simple. Y equals 36. That's the equation of the line that goes through the points of intersection of these two graphs with real coordinates. Okay, so I do want to show you a visual so you realize what you just found. All right, so here in blue we have y equals x squared, the first equation. In red we have x squared plus y squared equals 1332. We're showing part of it, of course it's a circle, right? You know that. All right, and notice in black we have the line that goes through the points of intersection of those two, the graphs of these two equations and of course the points of intersection of the solutions of that system with real coordinates. So there it is, the line y equals 36. So that's what you just accomplished. All right, let's go ahead and move on. All right, here's another application. We have a box with an open top, which has a square base. That means the length and the width of the base are the same. And 4 sides with equal height. So that means this height here is the same as well. The volume of the box is 275 cubic feet. If the surface area is 245 square feet, then find the dimensions of the box. All right, so there are a couple of things going on here. We need to know the formula for the volume, of course, because we're given the volume. It's 275 cubic feet. And we're also given the surface area, so we need that formula as well. Both of those happen to be pretty simple, right? It's a rectangular solid, so the volume is just, as you know, length times width times height, right? So the length and width are the same, so it's just going to be x times this height, which is common, which is y, right? So the volume is going to be x squared y, and we also know the surface area, so let's go ahead and start with that formula too, then we'll start substituting what we know. So notice that it has an open top, so you don't want to count the area that when you figure out the surface area, you don't want to count the area of the top because it's not there. So but the area of the base, that's just the square, so it's just going to be x squared, x times x, which is x squared. So the surface area is going to be x squared plus, and notice these 4 rectangles here, they're all going to have the same area because the length is x and the width, if you think about it as a width here, is y. So basically there's 4 of them, so 4xy. Okay, so notice that we know that the volume is 275, right? So we're going to say, I'm just going to write the x squared y on the left side, it's easier. So x squared y equals 275. And we know that the surface area is 245. So x squared plus 4xy should be equal to 245. Let me write it here so we can make a system out of it. All right, so that's the system we need to solve, right? So think about how you would approach that before you come back. All right, so I see that I can solve this pretty easily for y, right? So I'll do that. We get y equals 275 over x squared. So now if we substitute that, the 275 over x squared for y in the second equation, we should get an equation in x alone. So we get x squared plus 4x times 275 over x squared equals 245. And I'm going to simplify further. And we of course know x shouldn't be 0, but we expect that anyway. We're dealing with real measurements, right? They shouldn't be 0, otherwise the box would collapse, right? So now I notice that here the x's will cross cancel and leave me an x down below. So I need to know what 4 times 275 is. So 4 times 275, that's 1100, right? So plus 1100 over x, the x and x squared, just leaving an x down below. And on the other side, we have 245. So why don't we go ahead and move everything to one side. And we will go ahead and multiply both sides by x to clear the fractions. So we end up with x cubed plus 1100, because then the x's will cancel out, minus 245x equals 0. Let me put it in descending order. So x cubed minus 245x plus 1100 equals 0. All right, of all the equations we've seen so far, that does not look like a simple nut to crack, right? But you are in precalculus, you've learned quite a bit about finding zeros of polynomial functions, right? And this, after all, is a polynomial equation, isn't it? So we know that whatever solution this equation has, if it's rational, it's going to have to be quotients so that the numerator are factors of 1100 and the denominator factors of 1. So basically p over q, remember p are the factors of 1100 and q would be the factors of 1. Because that's 1, they're just going to be basically factors of 1100. So what are the factors of 1100? Let's take a look. Let's go ahead and find the prime factorization of 1100. So we get 1. No, I'm sorry. We never go with 1, right? 1 is not prime. So 2 gives us what? 550. And I'll just bring in our friend here to make sure we're doing these right, because we don't want to miss it because of some careless error. All right, so and then we know that that 2 should go again into that, and that gives us 275. Now, I always say before you try 5, you should try 3, but notice 2 plus 7 is 9 plus 5 is 14, which is not divisible by 3. So this number is not divisible by 3. So we go ahead and move on to 5. So we're going to divide that by 5. That gives us 55. And now we know 5 goes 11, and 11 gives us 1. All right, so the good news is there aren't that many factors, are there? 2, 5, 11, right? Well, of course, I mean, any combination or product of those will be factors too. But I'm saying as far as initial factors, we usually try, right? Otherwise, yeah, there are a whole lot of factors. You know, you can do 1100 itself. You can do 550, 275, 55. We don't need to worry about the negative cases, right? Usually we go plus or minus, remember, for P and Q. But here we don't need to do that because we're dealing with real measurements, right? They can't be negative. So I would say 2 is probably too small for our situation, right? My natural instinct would be to try 5 first. So that's what I'm going to do. So I'm going to go ahead and divide this polynomial by x minus 5, and I'll use synthetic division to see if 5 is going to be a solution of this equation. So let's go ahead and try to factor or divide. So we'll put 5 here. Now don't forget, this polynomial has a missing term, the square term, so we're going to use a 0 there. So 1, 0, negative 245, and 1100. So 1 drops down, so we get 1 times 5 is 5, and 0 gives us 5. That's 25. Negative 245 plus 25, that's negative 225. 5 times 225, 5 times 200 is 1,000, and 5 times 25. Let me just get some help here. All right, toward the end of the videos, my arithmetic brain shuts down a little bit, so I'm glad I did check that myself. So this is actually negative 220, and now we're going to multiply that by 5, which gives us negative 1100, and that is great news, because that means x minus 5 is indeed a factor of this polynomial here. So we can factor now as, so the x cubed minus 245x plus 1100 equals 0 can be factored as x minus 5 times whatever quotient this represents, which is what? Constant x squared. So 1x squared, or just x squared, plus 5x minus 220, and that should be equal to 0. All right, so I mean, we can try to factor that particular polynomial, but experience kind of tells me that's not factorable. I'm going to show you a way you can know for certain whether it's factorable or not. When we say that, we mean over the set of integers, okay? Or even rationals, right? So here's what you do. You go ahead and you find the discriminant. Remember, a is 1, b is 5, c is negative 220. So you find the discriminant, which is b squared minus 4ac. We've discussed this before. And that's going to give you 5 squared minus 4 times 1 times negative 220. Now, if this happens to be a perfect square, then this polynomial should be factorable. If it's not going to be factorable over the set of integers. All right, so let's try that. So we have basically 25, and negative times negative makes a positive, so plus 4 times 220. Now, I'm going to take the square root of that. And I notice it's not a perfect square. All right, so we go ahead and not waste any time. We'll move on to the quadratic. That's all. So we have x squared, x equals, well, either x minus 5 is 0, or x squared plus 5x minus 220 equals 0. So either x equals 5 or x equals, let me get rid of this stuff down here. I'm going to erase the factorization as well. So, or x squared, well, I'm going to go ahead and apply the quadratic. So negative 5 plus or minus square root of b squared, which is 25, minus 4 times 1 times negative 220 over 2 times 1, which is 2. So now we go ahead and bring our old friend back. So I'm going to go ahead and start with a fraction, then I'm going to go to the top. And I'm going to get rid of the A and S, which is the answer from the previous problem, which I don't want. Now I'm going to start typing. So negative 5. I'm going to do the plus case first. So plus the square root of 25, and I know that turns into plus, right? 4 times 220, and then over 2. And I'm going to hit enter. So I get 12.54, so I'll approximate to 12.5. So I get x is approximately 12.5. And now I'll do the minus case. So I'm just going to change that plus there to a minus. And that gives me a negative value, which I can't use. Remember, we're dealing with real lengths, right? Okay, so we reject this one. All right, so we have 2 possible x values that could be good. Now, if x is 5, that's going to make y which is 275 over x squared. It's going to be 275 over 5 squared, right? So that gives us 11. And if x is 12.5, that makes y equal to 275 over 12.5 squared. It gives us 1.76. Let's just round to 1.8. Be consistent, I guess. All right, so we have 2 possible scenarios. I'm going to put the solutions in this box up here, okay? So we can either say the box is either 5 feet by 5 feet by 11 feet, or that's if x is 5, or we can take the x equals 12.5 scenario, so it's going to be 12.5 feet by 12.5 feet by, notice the y in that case would be 1.8 by 1.8 feet. All right, so that's a pretty healthy problem there. Many skills we've learned came in handy, so make sure that you practice this, and then we'll proceed. All right, and here's the last problem we're going to look at today. Let the supply and demand equations for a certain commodity be the following. P equals square root of 0.1 q plus 36 minus 5, and the demand is P equals square root of 121 minus 0.1 q. First, we want to find the equilibrium demand. Basically, what that means is that to find the quantity in the demand function at the equilibrium point. So let me translate. That means find the quantity for the demand function at the equilibrium point. Now, the equilibrium point itself is a point at which the price and quantity will be the same for both supply and demand, right? So if we're looking at the equilibrium point, we're going to be able to put these two prices equal to each other, or solve that system. Basically, the system that we're going to want to solve is going to be the one containing p equals square root of 0.1 q plus 36 minus 5, and p equals the square root of 121 minus 0.1 q. Remember, both supply and demand are going to have their own graphs, and each one is going to have price and quantity in it, right? But at the equilibrium point, basically, that's where they meet. So that means they're both going to have the same price and the same quantity at that point. Now, both of these functions, they use the quantity as the independent variable and the price as the dependent variable. So they kind of look like that. But at this point, basically, at this particular P0, Q0 where equilibrium happens, they obviously have the same price and the same quantity. All right, so let's go ahead and try to solve this system. Now, obviously, because both of these expressions are equal to P, we can go ahead and set them equal to each other. So we get square root of 0.1 q plus 36 minus 5. Now, we've solved equations of this type before. You know that we need to go ahead and square both sides to try to eliminate the radicals. But of course, since there are two radicals involved here, we won't be able to do it all in one shot. So we're squaring both sides. So we end up with the left side, we just get 121 minus 0.1 q. On the right side, that's, remember, we're applying this formula, the square of a binomial, so f squared minus 2fl plus l squared. So the first one squared is just going to give us 0.1 q plus 36 minus 2 times 5 times that expression, so minus 10 radical 0.1 q plus 36, and then plus 5 squared, which is 25. All right, so at this point, we're going to go ahead and simplify both sides if they're not already simplified. And we notice there's a little bit we can do on the right side. It's best to simplify before you start moving things around. So we get 0.1 q, 36 added to 25, that should give us what, 50 and 11, so 61. All right, so now we'll go ahead and move the radical term right here to the left side. It becomes positive, so 10 radical 0.1 q plus 36 is equal to, and we'll move everything else to the right side. So 0.1 q plus 61 is already on the right side, and we also join plus 0.1 q minus 121 to the right side as well. Okay, so let's keep going with our simplification. So we get 10 radical 0.1 q plus 36 equals 0.2q, and then we're going to combine 61 and negative 121, and that should give us negative 60. All right, so we need to go ahead and square both sides again. And on the left side, because we still have a radical, right? So we're going to do this. So we end up with 100 times 0.1q plus 36. We've now eliminated the radical, and we're going to apply this formula again on the right side. So we get equals, now 0.2 squared should be 0.04, 0.04q squared minus, now we're doing 2 times 0.2 times 60. So that gives us 24. So 24q, and then plus 3600. So distributing the 100 on the left side gives us 10q plus 3600 equals 0.04q squared minus 24q plus 3600. So let's go ahead and move everything to the right side. So we get 0 on the left side, and we get 0.04q squared minus 24q plus 3600. That's already on the right side. Actually, let's not waste time. We see the 3600 on both sides, right? Let's go ahead and eliminate that. All right, so we get 0.04q squared minus 24q minus 10q is equal to 0. Oh, that makes things much easier, right? So we get, let me go ahead and erase this graph if you don't mind. All right, so we have 0 equals 0.04q squared minus 34q. Okay, let's go ahead and divide both sides by 0.04 to get rid of that coefficient, see what happens. Because on the left side, 0 divided by 0.04 is just 0. On the right side, we get, of course, this just becomes q squared. Remember, we're dividing by 0.04. Let's see what 34 divided by 0.04 gives us. 850. So we get minus 850q. All right, we're getting somewhere finally. Notice that I can factor out the q now, so that gives me q minus 850. So we either get q equals 0, which makes no sense. We're dealing with a commodity. We don't want to have no quantity, right? Otherwise, there's no business. All right. And the other possibility is that q minus 850 equals 0. So q equals 850. All right, so given that this is indeed the quantity for the demand at the equilibrium point, that is precisely the answer to the question part A. Now, to get the equilibrium price, you have options. You can take that and plug it into either of these, and you'll get the same answer. I'll plug it into here because it's easier. but you should go ahead and try it in there and convince yourself that you'll get the same thing. Remember, that's the equilibrium point at which price and quantity are the same for both demand and supply. All right, so for this part, we're just going to say P equals the square root of 121 minus 0.1 times 850. All right, so now we plug in the square root of 121 minus 0.1 times 850. And we get 6. All right, so that is the equilibrium price for this commodity, which is the price at the point of equilibrium. All right, so there you go. You know, a little bit involved, but if you're just patient and take your time, you'll be able to handle this stuff with no problem. All right, so you take care until the next time that we meet. And this, of course, was in dollars. Always give the final unit on the final answer. All right, we'll see you next time.